Right now, 100,000 invisible particles are passing through every square centimeter of your body. Not one of them touched you. Not one of them slowed down. You did not feel a single thing. And the most unsettling part is not that they exist. The most unsettling part is that we have known about them for decades, built entire underground laboratories trying to catch one, and we still cannot tell you what they are made of, where they came from, or what they want, if they want anything at all. For a long time, that was okay. Science is comfortable sitting with unanswered questions. We had bigger things to worry about, stars to map, planets to count, a universe to measure. So we built the most expensive, most powerful eye humanity has ever pointed at the sky. $10 billion, 20 years of work, thousands of scientists across 19 countries. The James Webb Space Telescope launched on Christmas Day 2021, unfolded itself in space like a piece of origami the size of a tennis court, and started sending pictures back to Earth. The first images were beautiful. Everyone cried a little. It felt like a victory. Then the data kept coming, and the more we looked, the more something felt wrong. Not broken instrument wrong, not calculation error wrong. The kind of wrong that means the story we have been telling ourselves about how the universe works might have a much bigger problem than anyone was ready to admit. Your phone works because of physics. The plane you flew on works because of physics. The medicine keeping people alive in hospitals right now works because of physics. So when the universe starts sending back data that physics cannot explain, the question is no longer just scientific. The question becomes personal. If the rules are wrong, what exactly are we standing on?
Before we get to what Webb actually found, we need to talk about why any of this matters. Because on the surface, it is easy to hear Space Telescope finds strange things and think, okay, that is interesting, good for the scientists, what is for dinner? But that reaction misses something important, something that connects the edge of the universe directly to the chair you are sitting in right now. Physics is not just a subject people study in school. Physics is the reason the world works at all. Every single morning when you wake up, you are surrounded by things that only exist because at some point someone figured out a rule about how the universe behaves, wrote it down, tested it 1,000 times, and then used it to build something. The screen you are watching this on, the electricity powering it, the car that got you home yesterday, the surgery that saved someone you love, all of it, every last piece runs on rules. Rules about how matter holds together, how energy moves, how forces push and pull. Take away the rules and none of it works. Take away the rules and you do not have medicine, you do not have aircraft, you do not have the GPS that told you to turn left 3 blocks ago. We have been building those rules for about 400 years. It started with people like Isaac Newton, who looked at a falling apple and saw a mathematical pattern hiding inside it. Then came others who figured out how electricity and magnetism work, how heat moves, how light travels. Each generation added another floor to the building. Each discovery made the next one possible. By the time we reached the 20th century, we had something extraordinary, a set of equations so precise, so reliable that we could use them to predict the behavior of particles smaller than atoms and objects larger than galaxies, all with the same handful of formulas. Scientists called it the Standard Model. It is the closest thing we have to a complete instruction manual for reality. Not perfect, they always knew that, but close enough to trust with human lives, close enough to stake entire civilizations on. So when James Webb launched and started sending data back, the plan was straightforward. Point the telescope at distant stars and galaxies, collect light that has been traveling for billions of years, run it through the Standard Model, and fill in the remaining gaps in our map of the universe. Confirmation work mostly, dotting the I's, crossing the T's. That is not what happened. In less than 2 years of operation, Webb produced more than a dozen findings that did not fit. Not findings that were slightly off, not readings that needed a small correction, findings that looked the standard model directly in the face and said no. Galaxies that could not exist at the age they existed, black holes that appeared before the things that were supposed to create them, a universe that seemed to be expanding at two different speeds at the same time, depending on how you measured it. Constants, the fixed numbers baked into the foundation of all our equations that appeared to be drifting. Each one of those findings on its own might be explainable. Instruments have errors, calculations get checked and rechecked. Scientists are careful people and they do not throw out 400 years of work because one number looks funny. But these were not one number. They kept coming. Different instruments, different teams, different methods, all pointing at the same uncomfortable conclusion. Somewhere in the building we have been constructing for 4 centuries, there is a crack. Not a hairline fracture you can patch over the weekend, a crack in the foundation, running deep, and the more carefully we look, the longer it gets. That is what makes Webb different from every telescope that came before it. Hubble showed us beauty. Webb is showing us something harder to sit with. It is showing us the places where our best understanding of reality stops making sense, the places where the map we drew does not match the territory. The question is not whether the crack is there. Webb has already shown us it is. The question is how deep it goes. And that question, it turns out, has everything to do with the most important problem humanity has ever tried to solve.
Let's start with something most people would rather not think about. Earth is not permanent. That is not a doomsday prediction or a science fiction plot. It is just a fact. The same way a fruit left on a counter has an expiration date. The sun, the same star that makes life possible on this planet, is slowly getting hotter. Over millions of years, that extra heat will make the oceans evaporate, the atmosphere thin out, and the surface become too scorched for anything to survive. On top of that, Earth's magnetic field, the invisible shield that protects us from the sun's radiation, has been weakening for centuries, slowly, quietly, like air leaking from a tire. Nobody alive today needs to worry about this. Nobody alive in the next 1,000 generations needs to worry about this. But at some point, the bill comes due. The question that serious scientists, space agencies, and governments have been wrestling with for decades is simple and terrifying in equal measure. When Earth stops working, where do we go? That question is not philosophy. It is engineering. It is astronomy. It is one of the most expensive, most urgent, most carefully worked problems in the history of science. Thousands of researchers have spent their entire careers on it. Billions of dollars have been poured into telescopes, missions, and calculations, all trying to answer one thing. Is there another planet out there that could keep us alive? For a long time, the honest answer was, we do not know. Space is vast. Most of it is empty. Most stars are the wrong type. Most planets we found were giant balls of gas with no solid surface, or frozen rocks with no atmosphere, or scorched wastelands too close to their star to support anything. The search felt endless. It felt, some days, like looking for a specific grain of sand on every beach on Earth at the same time. Then, in 2017, something changed. A telescope in Chile picked up a signal from a small, quiet star about 40 light-years away. 40 light-years sounds enormous, but in cosmic terms, it is practically next door. The star was called TRAPPIST-1, named after the telescope that found it. What made it extraordinary was not the star itself, it was what was orbiting it. 7 planets, 7 rocky, solid planets circling a single star. 3 of them sitting at exactly the right distance where temperatures could allow liquid water to sit on the surface, not too hot, not too cold. The zone scientists call habitable, the narrow band around a star where life as we know it becomes at least possible. The scientific community did not just notice this, they celebrated it. Here was a system with not 1, not 2, but 3 candidate planets that checked the most basic boxes: rocky surface, right distance, reasonable size. According to everything we understood about how planets form, those worlds should have atmospheres. When a rocky planet cools after forming, gases trapped inside the rock slowly escape to the surface: carbon dioxide, nitrogen, water vapor, the same process that gave Earth its first layer of air billions of years ago. The physics was clear, the math was straightforward. Those planets should be wrapped in a protective envelope of gas. They should have weather. They should have the conditions that make water possible. This was not wishful thinking. This was a calculation. Scientists do not get excited about hope. They get excited about numbers that add up. The numbers added up. For 6 years, TRAPPIST-1 was the best answer humanity had to the question of where we might go. Every paper published, every conference held, every mission planned around exoplanet research had TRAPPIST-1 somewhere near the top of the list. It became a kind of quiet symbol, a backup, a reason to believe the search was not hopeless. Then Webb pointed its instruments at the system, and the backup plan fell apart.
In 2023, Webb measured the heat coming off TRAPPIST-1b, the planet closest to the star. The method was precise. When a planet has an atmosphere, even a thin one, the heat from the star gets absorbed and spread around the whole planet, redistributed by wind and weather. The night side stays relatively warm because the air carries heat around. When Webb measured TRAPPIST-1b, it found nothing like that. The heat was sitting exactly where sunlight hit the surface and going nowhere. Bare rock, radiating energy straight into space with nothing to slow it down, nothing to spread it around. No gas, no air, no atmosphere of any kind. One planet, one disappointment. Scientists took a breath. Maybe it was an outlier. Maybe that particular planet had a bad history. Maybe the next one would be different. In 2024, Webb checked TRAPPIST-1c. Same instruments, same method, same result. Bare rock. Silence. The question that followed was not just what happened to these two planets. The question was what kind of force could reach across an entire solar system and strip two worlds completely bare. Worlds that by every rule we understood about planetary science should have held on to their atmospheres for billions of years. The answer Webb found was not a meteor strike. It was not some ancient catastrophe. It was the star itself. TRAPPIST-1 is a red dwarf, a type of star smaller and cooler than our Sun. Red dwarfs were considered promising precisely because they burn slowly and last for trillions of years, far longer than a star like our Sun. More time means more opportunity for life to develop. That logic made sense on paper. What the paper did not fully account for was the temper. Red dwarfs throw fits. They release sudden, violent bursts of energy, superheated streams of charged particles that blast outward in all directions. Every few hours, TRAPPIST-1 does this. Webb measured those bursts and found they were 12 times more powerful than any previous model had predicted. 12 times. Each blast hits the nearby planets like a pressure washer pointed at a sandcastle. Each blast strips away another thin layer of atmosphere. Over millions of years, there is nothing left. The cruelest part of the whole picture is this: the planets had to be close to survive. They needed to be in that narrow, warm zone where temperatures were right for liquid water. But being that close put them directly in the line of fire. The same distance that gave them a chance at life is what killed them. Too far, and they freeze. Close enough to be warm, and the star burns them clean. After Webb released that data, researchers went back and looked at the broader picture. They took every planet Webb had measured and plotted them on a simple chart. How much radiation a planet receives from its star on one side, how massive the planet is on the other. A clear line appeared. Above that line, holding on to an atmosphere is possible. Below it, the radiation wins. Almost every planet in the data fell below the line. Then came the number that changes the scale of the problem entirely. 75% of all stars in our galaxy are the same type as TRAPPIST-1, 3 out of every 4 stars. That means the planets most likely to exist in our galaxy are the ones most likely to be stripped bare by the very star they orbit. The most common solar system in the Milky Way is also, it turns out, one of the most hostile to life. Less than 8% of stars are like our Sun, stable, calm, consistent, warm without being violent, the kind of star that lets a planet keep its air for billions of years while life slowly figures itself out. We did not just get lucky with Earth, we got lucky with the Sun.
We are sitting on the one planet that worked, around one of the rare types of stars that does not destroy its own worlds, in a galaxy where that combination is the exception and not the rule. The backup plan was never just one system. The backup plan was the assumption that planets like Earth were common enough that we would find another one. Webb did not just close the door on TRAPPIST-1, it changed the odds on everything else.
So the backup plan is gone. The most promising address in the galaxy turned out to be a dead end. Fine, that is a problem for engineers and future generations to wrestle with. At least we still have time, right? At least the timeline is solid. At least we know how many years the sun has left, how long the universe continues, how much runway humanity has to figure the rest of this out. That is what most people assume, that even if the destination is uncertain, the clock on the wall is reliable. That the number scientists give you when they say the sun has about 5 billion years left is based on something firm, something tested, something we can trust the way we trust a wristwatch that has never once lost a second. Here is the problem. That number, and every number like it, comes from one single measurement. Not a family of measurements averaged together, not dozens of independent checks that all agreed. One measurement, the speed at which the universe is expanding. That is the clock. That is the only clock we have for questions this large. Get that number wrong, and every calculation built on top of it is wrong too. The age of the universe, how long before stars like our sun burn out, how far away distant galaxies actually are, how long before everything flies so far apart that the universe goes dark and cold and empty forever. All of it traces back to one number. For decades, scientists measured that number using a method that felt reliable. They looked at a specific type of exploding star, a kind that always explodes with roughly the same brightness. Because the brightness is predictable, you can use it like a measuring tape. You see how bright it looks from Earth, you compare that to how bright it should be, and the difference tells you how far away it is. Do that for enough of these exploding stars at enough different distances, and you can work out how fast the universe is stretching. The answer that kept coming back, checked and rechecked over years, was around 73. The universe expands 73 kilometers per second for every megaparsec of distance. That unit does not matter much for this conversation. What matters is the number, 73. A separate group of scientists came at the same question from a completely different direction. Instead of looking at exploding stars, they looked at the oldest light in existence. When the universe was very young, less than 400,000 years old, it was so hot and dense that light could not travel freely. Everything was a kind of glowing fog. Then the universe cooled just enough for that fog to clear, and light streamed out in all directions. That light is still traveling today. It is everywhere, a faint glow that fills the entire sky, left over from the first moment the universe became transparent. Scientists can study the patterns in that ancient light and use them to calculate how fast the universe has been expanding since the very beginning. Their answer was 67. 67 versus 73. At first glance, that sounds like a small difference, 6 units off, maybe a rounding error somewhere. Maybe one team made a mistake that would turn up on closer inspection. That is what everyone hoped. Both groups checked their work, then checked it again. Other teams looked at the data with fresh eyes. The gap did not close. Both methods were clean. Both results held up. The probability that the difference was just a random mistake, just noise in the data, just bad luck, came out to less than 1 in 3 million. In science, when you get odds like that, you stop calling it a coincidence. You start calling it a problem. This particular problem has a name. Scientists call it the Hubble tension. Tension because the two numbers are pulling against each other and neither one is willing to give way. The name makes it sound like a polite disagreement between colleagues. It is not. It is one of the most serious, unresolved conflicts in modern physics, because if both measurements are correct, then something is wrong with our picture of the universe at a very deep level.
Think about what it would mean for two completely different measuring methods to give you two completely different answers about the same thing. You ask one person to measure the length of a room using a tape measure. You ask another person to measure the same room using the angle of shadows at a specific time of day. One person says the room is 12 meters long, the other says it is 14 meters long. Both people did the work carefully. Both methods are valid in theory. Both have been used successfully many times before, but the answers do not match. The only explanations are that one of the methods has a hidden flaw nobody found yet, or the room itself is doing something strange, something that makes it appear different lengths depending on how you look at it. The universe might be doing something strange. One possibility that physicists have been considering is that something in the early universe, some kind of energy or force we haven't yet identified, was present in the first moments after the Big Bang and affected how the universe expanded during that time. If that force existed, it would throw off the calculations that rely on ancient light. It would explain why that method gives a different answer than the one based on exploding stars. It would mean our picture of the very beginning of everything is missing a piece. Another possibility is that dark energy, the mysterious force that makes up roughly 68% of everything in the universe and is responsible for pushing galaxies apart, is not constant. Most of our calculations assume it stays the same over time, a fixed background pressure built into the fabric of space. But there are hints, not confirmed yet but growing, that dark energy might be changing, getting stronger or shifting in some way we don't understand. If that is true, then the expansion of the universe is not a straight line we can trace forward and backward with confidence. It's a curve, and we don't know the shape of the curve. That matters enormously. Every timeline we have, every estimate of how long before the sun's light changes enough to threaten Earth, every calculation of how long the universe remains capable of supporting life anywhere, depends on knowing that curve. A wrong expansion rate doesn't just change one number on a chart, it changes the entire schedule. It could mean the universe is older than we thought, or younger. It could mean the window for life, the period when stars burn at the right temperature and galaxies hold together in the right way, is longer or shorter than any current estimate. Webb's role in all of this was not to solve the problem, it was to make the problem impossible to ignore. Before Webb, the two measurements disagreed, but the older instruments had enough uncertainty in their readings that you could tell yourself the gap might just be measurement noise. Webb is more precise than any telescope that came before it. When the Johns Hopkins team used it to study a gravitational lens, an effect where a massive object bends light from behind it like a giant magnifying glass, they got a clean geometric measurement with almost no room for the usual excuses. No complicated models, no assumptions about how stars behave, pure geometry. The answer was still 73. The gap did not close, it sharpened. There is something quietly unsettling about this that goes beyond the technical details. We have one clock for the universe, one way to measure how old it is, how long it will last, where we are in the story. That clock has been running for decades, and we trusted it. Webb looked at it carefully and found that depending on which side of the clock you read, you get a different time. The hands do not agree with the face. We do not yet know why. That is the honest answer. Some of the brightest people alive are working on it right now, checking measurements, building new models, searching for the hidden piece that makes both answers true at the same time. They haven't found it yet. Every new observation from Webb gives them more data to work with. So far, more data has meant more questions, not fewer. The clock is running. We just don't know exactly how fast.
There is a particular kind of uncomfortable feeling that comes when you are completely sure about something, and then reality quietly proves you wrong. Not in a small way, in a way that makes you go back and wonder how confident you ever had the right to be in the first place. That is where cosmology, the study of the universe as a whole, found itself after Webb started sending data. To understand why the discoveries in this section are so unsettling, you need a basic picture of how scientists thought the universe grew up. The story went like this.
Roughly 13.8 billion years ago, everything began in an event we call the Big Bang. In the first fraction of a second, the universe was unimaginably hot and dense, a churning soup of energy and particles with no structure at all. Then it started expanding and cooling. After about 380,000 years, the first atoms formed. After roughly 100 million years, the first clouds of gas began to collapse under their own weight, and the first stars ignited. Those early stars were enormous, far bigger than anything born today. They burned hot and fast, and when they died, they collapsed and exploded, scattering heavy elements into space, the iron and carbon and oxygen that would eventually find their way into planets and living things. From those first stellar explosions, over hundreds of millions of years, gravity slowly gathered gas and dust into larger and larger clumps. Those clumps became the early galaxies, small and irregular at first, merging and growing over billions of years into the massive structured spirals and ellipses we see in the universe today. The Milky Way took most of the universe's current age to become what it is. Other large galaxies did too. That was the timeline. It was not a rough sketch. It was a carefully constructed model built on decades of observation, mathematics, and cross-checking. Scientists had traced the light from ancient galaxies, measured their distances, studied their shapes, and the story held together. Small and chaotic early on, large and structured later. That was the sequence. That was the rule. Webb broke the rule on almost its first serious look at the early universe. When astronomers pointed Webb toward the most distant regions of space, they were looking back in time. Light takes time to travel. The light from a galaxy a billion light-years ago left that galaxy a billion years ago. The light from something 13 billion light-years ago left when the universe was still in its infancy. Webb's instruments are sensitive enough to capture that ancient light in detail that no previous telescope could manage. What they expected to find at those extreme distances was what the model predicted: small, dim, irregular proto-galaxies, the messy building blocks of the structures we see closer to home. What they found instead stopped researchers cold. Fully formed galaxies, large, structured, containing hundreds of billions of stars, sitting in the data at a point in time when the universe was only 300 to 500 million years old. By the model's own timeline, that was supposed to be impossible. You cannot build a galaxy of that size in 300 million years. The math does not allow it. The physics of how gas clouds collapse and stars form and gravity accumulates mass has a speed limit. Building something that large requires time, enormous amounts of it, billions of years of slow accumulation. Seeing it fully assembled at 300 million years is like finding a full-grown ancient oak tree that someone planted 3 weeks ago. Researchers checked the data. They checked it again. They looked for alternative explanations. Maybe the distance measurements were off. Maybe the light was being distorted in some way that made things look older than they were. Each alternative explanation got tested, and each one failed to fully account for what Webb was showing. The galaxies were real. They were where they appeared to be. They were as old as the data said. One team called them universe breakers, not as a joke, but as a genuine description of what they were doing to the existing model. The phrase spread quickly because it was accurate. Then came the black holes. A black hole is what happens when a massive star reaches the end of its life, collapses inward, and packs so much matter into such a small space that not even light can escape its gravity. That's the basic version. Supermassive black holes, the kind sitting at the centers of large galaxies, are thought to form through a longer process. The initial black hole from a collapsed star slowly feeds on surrounding gas and other matter over millions and billions of years, growing larger and larger until it reaches a mass millions or billions times greater than our Sun. The key word in that process is slowly. Growth takes time. You cannot rush it. The physics of how matter falls into a black hole has limits, known limits, that cap how fast even the hungriest black hole can grow. Scientists had calculated the maximum possible size a black hole could reach within any given time frame. Those calculations were solid. They had been tested against every black hole observation available. Webb found black holes that violated those calculations, not by a little, by orders of magnitude. At distances corresponding to the first few 100 million years of the universe, Webb detected black holes already containing masses equivalent to hundreds of millions or even billions of suns. By the accepted model of black holes' growth, those objects simply could not exist yet. There had not been enough time, not even close. The universe would have needed to be several times older than it was at that point for a black hole to grow that large through normal processes. The probability of these objects existing according to the models we had before Webb was effectively zero. Not approximately zero, not very unlikely. The models gave them no path to existence at all. Scientists have been forced to consider some uncomfortable possibilities. Maybe the very first black holes didn't form from dying stars the way later ones do. Maybe in the extreme conditions of the early universe, black holes formed directly from collapsing clouds of gas, skipping the star stage entirely and starting much larger from the beginning. Maybe they fed on matter faster than current physics says is possible through mechanisms we haven't identified yet. Maybe there's something about the structure of the early universe that accelerated the growth of both black holes and galaxies in ways that nothing in the current model accounts for. None of these possibilities are settled. All of them require adding something new to the picture, some missing piece that the model doesn't currently contain. What makes this pattern genuinely alarming, rather than just scientifically interesting, is that it's not isolated. Webb hasn't found one impossible galaxy or one impossible black hole. It's found them consistently, repeatedly, in dataset after dataset, in different parts of the sky, observed by different research teams using different methods. Every new image from the deep universe seems to contain at least one thing that should not be there yet. The pattern has become so consistent that it's no longer reasonable to blame instrument error or bad luck. Something in the early universe was working faster, building bigger, assembling structure at a pace that nothing in our current understanding can explain. The timeline we built, the history of how everything grew from simple beginnings into complex structure, has gaps in it that weren't visible before Webb. Large gaps, the kind of gaps that suggest the story we were telling was missing entire chapters. The history of the universe is older than we thought, or more efficient than we thought, or governed by forces we haven't named. Possibly all three. Webb keeps sending data, the gaps keep growing, the model keeps bending under the weight of what the telescope finds. Something out there was building the impossible long before we had the tools to see it, and now that we can see it, we have to admit we don't yet understand how any of it was done.
When scientists encounter something they cannot explain, they do not usually panic. They do what scientists do. They look for an explanation that fits inside the existing picture, something that patches the gap without requiring them to throw out everything they already know. It is a reasonable strategy. Most of the time, the gap turns out to be smaller than it first appeared. When the impossible galaxies and the two early black holes started showing up in Webb's data, researchers reached for the most powerful explanatory tool in modern physics, dark matter. It was a natural move. Dark matter had already saved the model once before, decades ago, when astronomers noticed that galaxies were spinning in ways that made no sense. The outer edges of galaxies were moving just as fast as the inner regions, when by all rights they should have been slower. The math of gravity said they should fly apart. They did not fly apart. Something was holding them together, something with mass and gravitational pull, but no light, no radiation, nothing detectable by any instrument pointed at the sky. Scientists called it dark matter. Not because they knew what it was, but because they needed a name for the invisible thing that was clearly there. The evidence for dark matter has piled up over decades. Not direct evidence. Nobody has ever caught a dark matter particle or seen one in a detector. The evidence is all indirect, the gravitational fingerprints it leaves on the things we can see. Galaxies rotate the way they do because of it. Light bends around clusters of galaxies in patterns that only make sense if enormous amounts of invisible mass are present.
The large-scale structure of the universe, the way galaxies clump into filaments and sheets and walls separated by vast empty voids, matches what computer simulations predict only when dark matter is included. Take it out of the simulation and the universe looks nothing like the one we observe. Put it back in and everything snaps into place. So dark matter is real in the sense that something is definitely out there doing a job. What that something actually is, what it is made of, whether it is a single type of particle or many types, or something stranger still, nobody knows. The experiments built to detect it directly, enormous tanks of liquid buried deep underground to shield them from interference, have been running for years. They have found nothing. The searches keep getting more sensitive. The silence keeps stretching. Now add a second invisible ingredient: dark energy. Dark energy is even harder to picture than dark matter. At least dark matter behaves something like ordinary matter. It has mass, it gravitates, it clusters. Dark energy is different in kind. It does not pull things together, it pushes them apart. It is a property of space itself, a kind of built-in pressure that causes the universe to expand, and not just expand, but accelerate. The farther apart two regions of space are, the faster they are being pushed away from each other. Eventually, if this continues, galaxies beyond a certain distance will be moving away from us faster than light can cross the gap. They will simply vanish from any possible observation. The universe will grow lonelier and darker and emptier as time goes on, not because matter is being destroyed, but because everything is being pushed beyond reach. Dark energy makes up roughly 68% of everything. Dark matter makes up about 27%. All the ordinary matter in the universe, every star, every planet, every atom of every person who has ever lived, adds up to about 5% of the total content of the cosmos. We are the footnote. The universe is mostly made of things we cannot see, cannot touch, cannot identify, and in the case of dark energy, cannot even meaningfully describe except by what it does. That would already be a humbling situation. Then Webb found something that made it worse. Buried in the light from distant quasars, which are enormously bright objects powered by black holes at the centers of ancient galaxies, Webb detected something subtle. The light from those quasars had been traveling for billions of years before reaching the telescope. Along the way, it passed through clouds of gas, bounced around structures in intergalactic space, and carried with it information about the conditions it had traveled through. When researchers analyzed the fine details of that ancient light, they found hints that one of the most fundamental numbers in physics might not be the same today as it was billions of years ago. The number in question is something called the fine structure constant. The name doesn't matter much. What matters is what it does. It controls how strongly electrically charged particles interact with each other. That interaction is the basis of chemistry. It determines how atoms bond together, how molecules form, how energy moves through matter. Every chemical reaction that has ever happened anywhere in the universe, including every reaction happening right now inside your body, runs on that number. It's not just a scientific curiosity, it's the reason matter does anything at all. The assumption baked into every equation in physics is that this number never changes. It is a constant. That's what the word means. It was the same a billion years ago as it is today. It will be the same a billion years from now. That assumption has been checked many times in the local universe, and it has always held. Nobody had the tools to check it across truly vast stretches of time and space. Then Webb arrived. The signal in Webb's data is not yet confirmed. Researchers are careful to say that. It's a hint, a pattern in the numbers that could still turn out to be noise or a subtle measurement error. Other teams are checking it. More data is being gathered. But the pattern is there, and it is consistent enough that serious physicists are taking it seriously, writing papers about it, building new calculations around the possibility that it might be real. Think for a moment about what it would mean if it is. A constant that changes is no longer a constant, it's a variable. A number that was different in the past and might be different in the future. The equations that use it as a fixed input would need to be rewritten with a time-dependent value instead.
Every prediction those equations make would shift. The chemistry of the early universe would have been different from the chemistry of today, perhaps in small ways, perhaps in large ones. The conditions that allowed atoms to form, that allowed stars to ignite, that allowed life to build itself out of carbon and water and nitrogen might have been operating under a slightly different set of rules than the ones operating right now. Your medications work because chemists calculated exactly how molecules would interact under the current rules. Aircraft fly because engineers calculated exactly how materials behave under current physical conditions. The GPS signal that navigates you home works because physicists accounted for exactly how time and light behave in current laws. All of that depends on the constants staying constant. If they drift, the drift is presumably very small, so small that nothing built on human timescales would notice. But the universe operates on timescales that make human history look like a single heartbeat, and on those timescales, even a tiny drift accumulates into something significant. The universe we thought we lived in was 95% invisible, but at least governed by stable, reliable rules. Webb is raising the possibility that even the rules are not fully stable. The 5% we can see, the matter we're made of, and the stars we navigate by, is riding on a foundation that might be shifting underneath it, slowly, across billions of years, in ways we are only now beginning to detect. That is not a comfortable thing to sit with. It was not supposed to be in the data. Nobody designed Webb to look for drifting constants. It found the hint anyway, the way good instruments tend to find things nobody thought to look for, because the universe doesn't limit its surprises to the questions you remembered to ask.
Of all the things Webb has shown us, this one sits differently. The others are frightening in a cold, mathematical way. Galaxies that should not exist, a clock that might be broken, constants that might be drifting. Those findings are unsettling because they threaten the framework we use to understand everything else. But this one is unsettling in a more personal way. This one touches the question that human beings have been asking for as long as we have been capable of asking questions at all. Are we alone? Before we get to what Webb found, it helps to understand what scientists thought they knew about the ingredients for life. For a long time, the working assumption was that life is chemically demanding. The molecules that make up living things, the long chains of carbon atoms, the amino acids that build proteins, the complex organic compounds that store and transmit information, were thought to require very specific conditions to form: a planet, liquid water, a stable environment where chemistry could run its slow experiments over millions of years without being blasted apart by radiation or frozen into stillness. Life, in this view, was the product of a rare and lucky combination of circumstances. The ingredients were not the hard part, the cooking environment was. That assumption started cracking decades before Webb launched. Astronomers had already found simple organic molecules drifting in space, things like formaldehyde and methanol and ethanol, basic carbon compounds floating in the clouds of gas and dust between stars. Interesting, but not shocking. Simple molecules form under simple conditions. Nobody was particularly surprised. Then, the molecules kept getting more complex. By the time Webb launched, the list of organic compounds detected in interstellar space had grown long enough to raise eyebrows. Sugars, amino acids, the exact building blocks that proteins in living cells are made from, found in meteorites that had drifted through space for billions of years before landing on Earth. Complex ring-shaped carbon molecules that show up in biological systems. The precursors, the raw chemical ingredients that life on Earth uses as its starting materials, turning up in places where no planet existed, no ocean sat, no warm pond bubbled quietly under a young sun. Webb took this further than any instrument before it.
Pointing at young solar systems and the process of forming, Webb detected complex organic molecules embedded in the disks of gas and dust swirling around newborn stars. These are the disks that eventually become planets. The organic chemistry is already there before the planets finish forming. It arrives as part of the package, baked into the material from which worlds are built, delivered wholesale from the interstellar clouds where stars and their surrounding systems are born. Pointing at regions between star systems, Webb found the same chemistry assembling itself in the cold dark between the stars, in places where temperatures drop to within a few degrees of absolute zero, where no energy source obvious enough to drive chemistry should exist. The molecules were there anyway, quietly building themselves in conditions that should have been too hostile for anything to happen. The picture that emerged from this was startling in its implications. The raw materials of life are not rare. They are not special products of unusual planetary chemistry or exotic geological conditions. They are standard outputs of the universe's ordinary processes. Wherever carbon and hydrogen and oxygen and nitrogen come together under the right physical conditions, which apparently includes quite a lot of the galaxy, complex organic chemistry follows. Not always, not inevitably, but regularly enough that these molecules are scattered across interstellar space like flour dusted across a kitchen counter. The universe is not just capable of producing the building blocks of life, it produces them routinely, in bulk, spread across billions of light years of space without any particular effort or any special circumstances. The factory runs continuously. The raw materials are everywhere, which makes the silence deafening. Because life itself, actual living things, things that take those ingredients and use them, things that grow and respond and reproduce and eventually look up at the sky and wonder what is out there, we have found exactly one example, one planet, one biosphere, one data point in the entire observable universe. This is what scientists call the Fermi paradox, though paradox might be too gentle a word for it. The universe is roughly 14 billion years old. It contains hundreds of billions of galaxies, each containing hundreds of billions of stars, a significant fraction of those stars orbited by planets, many of those planets sitting at distances where liquid water could exist. The organic chemistry needed to start life appears to be standard equipment delivered during planetary formation. The time available for life to develop and spread is almost incomprehensibly long. Even if life only arose on 1 in a million planets, even if intelligent life only arose on 1 in a billion of those, the sheer number of opportunities means the galaxy should, by the math, be full of it. Old civilizations, young ones, ones that have been spreading for billions of years, the silence should not be possible. The silence is total. Not a single confirmed signal from another civilization, not a single unambiguous biosignature on another world, not a single piece of evidence, despite decades of searching with increasingly sensitive instruments, that anything in the universe has ever used those organic molecules the way life on Earth uses them. Webb has sharpened this problem rather than solved it. It has shown us that the ingredients are even more widespread than we thought, that the universe is even more generous with its chemical raw materials than previous observations suggested. Every new data set makes the raw material side of the equation more favorable. Every new data set leaves the outcome side exactly where it was. One example: us. There are several ways to think about this. The optimistic interpretation is that we have simply not looked carefully enough yet, that life is out there in abundance, and we lack the tools to detect it from here. Webb is already beginning to analyze the atmospheres of planets around other stars, searching for chemical signatures that would suggest biological activity. That work is in its early stages. The absence of a confirmed detection so far means nothing definitive. A darker interpretation is that something goes wrong between having the ingredients and producing life, that the step from complex chemistry to the first self-replicating molecule is not just difficult, but extraordinarily rare, perhaps so rare that it has only happened once in the observable universe, here, on this particular planet, around this particular star, at this particular moment in cosmic history. In this view, the ingredients being common makes the emptiness more haunting, not less, a universe full of kitchens and no meals. A third possibility, perhaps the most unsettling, is that life arises more commonly than we think, but something stops it from persisting or spreading. The hostile stars that stripped TRAPPIST-1's planets bare, the expanding universe pushing galaxies beyond communication distance, the deep time gaps between civilizations that arise and fall before they ever have the chance to find each other, a filter somewhere in the chain between chemistry and contact that most life never crosses. Webb cannot tell us which interpretation is correct. What it has done is remove one of the remaining excuses for hoping the problem was simpler than it looks. The excuse used to be that maybe organic chemistry was rare, that the building blocks of life required unusual conditions, and most of the universe simply lacked the right materials. That excuse is gone now. The building blocks are everywhere. The universe has been generous beyond any reasonable expectation with everything life needs to get started. What the universe has not been generous with is the outcome. The kitchen is fully stocked, the counters dusted with ingredients that have been falling through space for billions of years, assembled automatically in the dark between stars by processes that require no guidance and no special conditions. The recipe is written into the chemistry of the cosmos itself. Something is missing between the ingredients and the meal. Webb has made that gap more visible than ever and more difficult than ever to explain away.
Step back for a moment from the individual findings. The stripped planets, the broken clock, the impossible galaxies, the drifting constants, the silent kitchen full of unused ingredients. Each one of those is striking on its own. But when you line them up and look at them together, they are telling a single coherent story. Not a story about specific mysteries waiting to be solved, a story about the overall direction the universe is heading and where we sit in that arc. The universe is winding down. That is the picture Webb has been assembling, piece by piece, with every dataset it sends home. Start with the stars. Stars are the engines of everything. They are the furnaces that cook hydrogen into heavier elements, the carbon and oxygen and iron that eventually find their way into planets and oceans and living cells. When a star is born, it burns for millions or billions of years, depending on its size, pouring energy into the space around it, warming anything close enough to benefit. When it dies, it scatters its contents outward, seeding the next generation of clouds and planets, and eventually life. Stars are not just light sources, they are the mechanism by which the universe builds complexity out of simplicity. For the universe to keep building complexity, it needs to keep making stars. New stars require raw material, vast clouds of cold gas, mostly hydrogen, drifting in the spaces between existing stars and galaxies. Gravity gathers those clouds, compresses them, heats them until the pressure at the center becomes great enough to ignite nuclear fusion and a new star is born. That process has been running since the universe was a few 100 million years old. It has produced more stars than there are grains of sand on every beach on Earth, more than most people can begin to visualize. The process is slowing down. Webb's observations confirm what earlier telescopes had begun to suggest. The rate at which new stars form has been declining for billions of years. The universe was making stars most aggressively about 10 billion years ago, churning them out at a pace that dwarfs anything happening today. Since then, the rate has been falling, gradually but consistently, like a fire working through the last of its fuel. The raw material is running out.
The cold gas clouds that gravity needs to compress into new stars are being used up faster than they are being replenished. Stars that exist now will burn out over billions or trillions of years. Fewer new ones will replace them. Eventually, the last star will form, burn for its allotted span, and go dark. After that, no new ones will follow. The universe is not in immediate danger of running out of stars. The timescales involved are enormous, far beyond anything that touches human concerns. But the trend is real, the direction is clear, and Webb has made it measurable with a precision that was not possible before. We are living in a universe past its peak of star formation. The golden age of star birth is behind us, billions of years behind us. What we have now is the long, slow afternoon of a cosmos that was most alive and most active long before Earth existed. While that slow decline continues in the background, the foreground is considerably more violent. Galaxy collisions are not rare events in the universe. Galaxies are not fixed objects sitting quietly in assigned spots. They move, they drift, they get pulled by each other's gravity, and when two of them get close enough, they do not pass through each other like ghosts. They interact dramatically over hundreds of millions of years. Their stars rarely collide directly because the distances between individual stars are so vast, but the gas and dust within them gets disrupted, compressed, flung into new configurations. The gravitational forces reshape both galaxies entirely, pulling long tails of stars out into space, triggering enormous bursts of new star formation in the compressed regions, and eventually, if the collision is strong enough, merging the two galaxies into a single new one with a different shape and character than either of its parents. Webb has been watching these collisions in detail that no previous telescope could manage. The images are extraordinary, two spiraling structures reaching toward each other across hundreds of thousands of light years, their arms beginning to intertwine, rivers of gas and dust being drawn between them like taffy being pulled in two directions at once. In the regions where the gas gets compressed by the collision, Webb detects bursts of new star formation, a temporary spike in the birth rate caused by the disruption. Those bursts are dramatic but short-lived on cosmic timescales. After the merger completes and the combined galaxy settles into a new stable shape, the star-forming burst fades and the long decline resumes. Our own galaxy will experience this. The Milky Way is currently on a slow collision course with the Andromeda Galaxy, our nearest large neighbor, roughly 2.5 million light-years away. The collision will begin in about 4 billion years. Long after the Sun has started to change in ways that threaten Earth, the galaxy itself will be in the process of being torn apart and rebuilt. The night sky of that distant era, if anything is left to observe it, will look nothing like the one we see tonight. Then there is the dust. Cosmic dust sounds like a minor detail. It is not. Dust is the solid material that makes planets. It is the condensed remnants of dead stars, the heavy elements forged in stellar cores and scattered by stellar explosions, cooled and solidified into tiny grains drifting through space. When a new solar system forms, the dust in the disk around the young star clumps together, grain by grain, pebble by pebble, boulder by boulder, eventually building the rocky planets that orbit close to the star. Without dust, you don't get rocky planets. Without rocky planets, the particular kind of life we are familiar with has nowhere to take hold. Scientists had a timeline for when dust should have appeared in significant quantities in the universe. It required stars to form first, burn through their fuel, die in explosions, and scatter their enriched material into space. That process takes time, hundreds of millions of years at minimum. The dust we are made of should be a relatively late product of the universe's chemistry, something that accumulated slowly over billions of years. Webb found dust in the early universe long before the timeline allowed for it. Ancient galaxies observed by Webb contain dust in quantities that should not have been possible given how young those galaxies were. Something in the early universe was producing and accumulating solid material far faster than the model predicted. How exactly remains an open question. The timeline for when the raw materials of planets became available across the universe has been pushed back significantly, which in turn pushes back the timeline for when rocky planets could have formed, which in turn changes the window during which life might have had the opportunity to arise anywhere in the cosmos.
Beyond the dust, Webb has been detecting something else drifting in the spaces between stars. Objects that do not orbit any star, that are not part of any solar system, that is simply out there in the dark between stellar neighborhoods, wandering alone in interstellar space. Some of these are planet-sized, some are smaller. They were not predicted in large numbers by existing models. Webb keeps finding them, in quantity, suggesting that the spaces between stars are more populated with free-floating material than anyone had calculated. The galaxy is not the relatively clean structure we imagined, stars with their ordered planetary families spaced across a dark background. It is littered with wanderers, objects that formed in one context and ended up in another, or that were never part of any organized system at all. Everything Webb shows us about the current state of the universe points in the same direction. The peak is past. The great burst of creation, the era when stars formed in abundance and galaxies built themselves into complex structures and the raw materials of planets and life spread through every corner of the cosmos, that era is behind us. What we have now is the long, slow afternoon of a cosmos that was most alive and most active long before Earth existed. While that slow decline continues in the background, foreground is considerably more violent. The universe is not dying quickly, it is aging quietly, the way an enormous fire ages, still burning, still warm, still capable of remarkable things in the right places at the right moments, but past the point where it was adding fuel faster than it was consuming it. The embers are spread across 100 billion galaxies. They will glow for an almost incomprehensible span of time, but the direction of travel is set. The universe is in its long evening, and Webb, with its extraordinary eye, is the first instrument precise enough to see the color of the light changing. We exist in that evening, not at the end, not anywhere close to the end, but well past the morning. That is where we are in the story. That is the context for everything else this telescope has found. There is a moment in Webb's short history that deserves more attention than it usually gets. Not a discovery exactly, not a measurement or a data point or a finding that overturned a model. Just a photograph. The first deep-field image Webb released to the public in July 2022. To take that image, Webb stared at a single patch of sky for an extended period of time, collecting every photon of light that passed through its mirrors from that direction. The patch of sky it chose was tiny. Hold a grain of sand at arm's length against the night sky. The area that grain covers against the backdrop of space is roughly the size of the region Webb photographed. A sliver, a fragment, an almost insultingly small sample of the total sky above us. When the image came back, it was filled, edge to edge, corner to corner, packed with light. Not stars, galaxies, thousands of them, each one containing hundreds of billions of stars, each of those stars potentially orbited by planets, some of those planets sitting at the right distance from their star for liquid water to exist on the surface. All of that compressed into a patch of sky smaller than a grain of sand held at arm's length. The first time most people saw that image, something shifted. Not just scientifically, something deeper. The kind of shift that happens when a number you knew intellectually suddenly becomes real in your gut. We knew the universe was large. We knew it contained a lot of galaxies. Those facts had been in textbooks for decades. But knowing a fact and seeing it are different experiences entirely. The image made the scale real in a way that no statistic had managed before. Webb has taken hundreds of images since then. In every direction it points, the result is the same. More galaxies, more structure, more complexity stacked behind complexity, layer after layer of light from objects billions of light years away, all of it arriving simultaneously at the telescope's mirrors after journeys of varying lengths across the expanding universe. The universe is not mostly empty space punctuated by the occasional galaxy. It is a dense web of structure, and the emptiness we perceive when we look up at the night sky is mostly a consequence of our limited eyes, not a reflection of what is actually there. But the deep field image does something else that takes longer to appreciate. It is not just a demonstration of quantity, it is a compressed archive of everything Webb has spent 3 years finding, all of it present in a single frame, if you know how to read it. Look at the bright objects closest to us in that image, the ones whose light has traveled the shortest distance to reach the telescope. Among them are galaxies in various stages of their lives, some still actively forming stars, their blue-white regions glowing with the light of young stellar furnaces, others older and redder, their star formation slowed or stopped, their populations of stars aging together like a generation that has stopped having children. The full life cycle of a galaxy compressed into a single field of view. Look deeper into the image, at the objects whose light has traveled further, and you were looking further back in time. The galaxies at middle distances show the universe as it was several billion years ago, when star formation was more active, when collisions between galaxies were more frequent, when the structures we see around us today were still assembling themselves. You can see the collisions happening in that image, pairs of galaxies caught in the slow gravitational embrace that will eventually merge them into something new, their shapes distorted by the forces pulling at them, long tails of stars stretched out into the surrounding space. Look at the most distant objects in the frame, the faint red smudges at the very edge of what the telescope can detect, and you are seeing light that left its source when the universe was only a few 100 million years old. These are the objects that have caused the most trouble for the existing models, the galaxies that should not yet exist, the structures that assembled too quickly for the timeline to accommodate. They are right there in the image, easy to miss because they are small and faint, but present, each one a quiet challenge to the physics textbooks. Scattered throughout the image, detectable not visually but through the spectral analysis Webb performs on the light it collects, are the chemical signatures of the organic molecules discussed earlier, the building blocks of life, drifting in the spaces between galaxies and between stars, present in the disks around young stellar systems caught in the process of building their planets. The kitchen stocked with ingredients, spread across every corner of the frame. The gravitational lensing that gave the Johns Hopkins team their clean measurement of the expansion rate is visible in that image too. Galaxies in the foreground, massive enough to bend the light passing near them, have distorted the images of galaxies behind them into stretched arcs and smeared rings. Those distortions are not defects in the image. They are the geometry of space-time made visible, the direct consequence of mass bending the path of light as it travels across billions of light years. The same effect that provided one of the two disagreeing measurements of the expansion rate, the discrepancy that suggests something fundamental is missing from our understanding, is written into the fabric of the image. The dust that appeared too early in the universe's history, the dust that pushed back the timeline for when rocky planets became possible, shows up in the image as dark lanes cutting through certain galaxies, the solid material absorbing the light behind it and casting shadows visible across intergalactic distances. The stars that are dying faster than new ones are born show up as the older, redder populations in the elliptical galaxies, the ones that have used their gas and stopped producing. The free-floating objects drifting between stars, the wanderers that Webb detected in such unexpected numbers, are not visible individually in an image like this, but their existence is implied by the same processes that created everything else in the frame. Every single major finding from Webb's first 3 years of operation is encoded somewhere in that image. The impossible structures, the broken timeline, the chemical abundance without biological outcome, the invisible majority of the universe making its presence felt through gravitational effects on the visible minority, the collisions and the dust and the wanderers and the slow dimming of star formation across cosmic time. All of it in one photograph, covering a patch of sky the size of a grain of sand. That fact, once it settles in, changes how you read the image. It stops being a beautiful picture of faraway things and becomes something more like a complete statement, a single frame that contains the full complexity of what we have learned and what we do not yet understand, presented simultaneously, without hierarchy, without the narrative structure of a documentary or a lecture where one thing leads to another in an ordered sequence. The universe does not organize its contents for our convenience. Everything is happening at once, in every direction, at every scale, all the time. Webb was built to look far. What it found when it looked far was not distance, it found depth. Not the depth of space, though that is certainly there, the depth of the question. Every image it has returned has added another layer to the same fundamental puzzle, a universe that is extraordinarily good at producing the conditions for complexity, for chemistry, for structure, for the precursors of life, sitting in near total silence when it comes to the outcome of all that preparation. The grain of sand aimed at the sky contains thousands of galaxies. Each of those galaxies contains hundreds of billions of stars. Each of those stars is a furnace running the same chemistry that built every atom in your body. The scale of it is genuinely impossible to hold in the mind at all once. The human brain did not evolve to process numbers this large or distances this vast. We understand them intellectually, the way we understand that a trillion is bigger than a billion, without being able to feel the difference. But the image does something the numbers cannot. It makes the scale visible in a single glance. One look, one moment of taking in what is actually there in that frame, and the abstract becomes concrete. Not comfortable, not reassuring. The image is not designed to comfort. It is designed to show what is there. What is there happens to be everything Webb has found, assembled into a single field of view, covering less sky than a grain of sand, reminding anyone willing to sit with it that the universe is not a backdrop. It is the whole story, and we are somewhere in the middle of it, still figuring out what we're looking at.
So after 3 years and 41 discoveries, what has Webb actually given us? It showed us that the planet we need to leave is orbiting one of the rare stars that does not destroy its own worlds. It showed us that the best backup options we found are bare rock, stripped clean by the very stars that were supposed to warm them. It showed us that the clock we use to measure how much time is left might be giving us 2 different answers at the same time. It showed us that the ingredients for life are scattered generously across every corner of the cosmos, and the outcome of all that generosity is, as far as we can tell, one small planet in one unremarkable corner of one ordinary galaxy. It showed us that 95% of everything is invisible, unnamed, and only detectable by the shadows it casts on the 5% we can see. It showed us that the rules we depend on to predict what happens next did not hold at the beginning of the story and may not be holding perfectly right now. That is a heavy list. Nobody would blame you for finding it overwhelming. But here is the thing Webb showed us that it never intended to show, the thing that does not appear in any scientific paper or press release or data archive. Across 13.8 billion years, across 100 billion galaxies, across distances so vast that the numbers lose all meaning before you finish saying them, the only thing we know of that has ever looked at all of it and felt something about it is you. Not humanity in the abstract, not a species or a civilization or a collective achievement. You, specifically, the person absorbing this right now, made of carbon forged in dead stars, sitting on a temporary planet in the evening light of a universe past its peak, choosing to look outward and ask what is there. Webb did not build itself. The universe did not decide to understand itself. You did that. Something assembled from ancient stellar debris pointed a mirror at the edge of time and refused to look away, even when the answers came back dark and strange and uncomfortable. That is not a small thing. In a universe this large and this old and this indifferent, the fact that any part of it became curious about the rest is perhaps the strangest discovery of all. Webb gave us perspective, not comfort, not reassurance, not a reason to stop worrying about the things that fill ordinary days. Perspective. The kind that does not make your problems disappear, but places them inside a frame large enough that their actual size becomes visible. Whatever you are carrying right now, you are carrying it inside the one window of time when the stars are still lit, the chemistry is still running, and the light from the very beginning of everything is still arriving. That window is smaller than Webb showed us we thought it was. It is also, right now, open. 41 discoveries. One question no telescope can answer. What do you do with all of this?
Leave it in the comments. Not what you know, but what you think. What changed for you? What did not? If this made you see something differently, hit the like button. And if someone in your life needs to hear this, send it to them. Some things are too large to sit with alone.